Okay, kids. Algebra 2 students, our sequence and series word problems and logarithms revisited. And actually, it's funny because when I finish the word problems, it turns out I actually need to use a logarithm to solve one of them. But anyway, I thought you'd appreciate this. I thought this was pretty funny. He's pretty excited over his little, not really a fallacy, just sort of an anomaly of dealing with these repeating decimals. So anyway, let's jump right in and let's solve the 6 word problems that were sent home with me. Okay, so we're going to start with this first one. A contractor must pay a penalty if work on a project is not completed on time. The penalty on the first day is $300. The penalty increases up to $500 on the second day, $700 on the third day, and so on. So the first thing we should be recognizing here is which type of sequence we're dealing with. And this is indeed arithmetic. And the common difference here is 200. And the first value, or the first term, is 300. All right, so it's an explicit formula for this sequence. It's going to look like this. There we go. First term, plus n minus 1, the quantity times the common difference. So that's going to be our explicit formula. We usually go ahead and simplify the right-hand side. So 300 plus 200n minus 200. 300 minus 200 is 100. 200n plus 100. Okay? So the contractor got a penalty of $4,500. How many days after the due date was the project completed? Well, we're going to use our formula, and we're going to put 4,500 in for n. And we are finding n. So 4,500 equals 300. Oh, no, let's not do that. Let's use our formula just above. Silly. 200n plus 100. Easy to solve. Subtract 100. We've got 4,400 equals 200n. Divide by 200. 22. 22 days late. Okay, so I guess it does make sense to hold kids to deadlines, because the real world holds you to deadlines too. Let's look at the next one. Table tennis rules regulate the specific properties for the table, the ball, the net, and the paddles. According to the rules, a ball dropped from 30 centimeters above the table surface must bounce back to the height of 23 centimeters. This ratio of the drop height to the bounce height remains the same for any 2 consecutive bounces. Write the first 5 terms of a sequence that describes the bounce heights after an initial drop of 30 centimeters. Round your answers to the nearest tenth. Okay, so we know it starts with 30. And the second one is 23. And every single one after that, we multiply by 23 over 30. It's an awkward fraction, so the decimals are going to be rather long, and they are repeating decimals. So I went through and just kept multiplying by that common ratio and rounding off the answer to the nearest tenth as directed in the problem. An explicit formula for this would be an equals a1, which is 30, times r, which is 23 thirtieths, to the quantity n minus 1. Okay? Third problem. A fruit fly receives genetic material from 2 parents. Each parent also receives genetic material from 2 parents. So each fruit fly receives genes from 4 grandparents, 8 great-grandparents, and so on. How many ancestors does a fruit fly have going back 15 generations? So we've discovered, or we've seen that powers of 2, that grows very quickly. So this is an interesting sequence to think about. First of all, let's state what it is. It's going to be geometric. Kind of neglected to even discuss that in problem number 2, but I figured you probably picked up on that pretty quickly once we started using the geometric formulas. A1 here is going to be 2. AN is what we're finding, so I'm going to put AN question mark. The common ratio here is 2, because if the first term is 2, the second term is 4, these are the numbers going back in terms of generations, but it's going forwards in our sequence, and we're multiplying by 2 every time. So that's our ratio. And then in this case, n is going to be 15. So start with our formula. And we have 2 times 2 to the 15 minus 1. 2 times 2 to the 15 minus 1. And that's finding A15. Okay, so really what's happening here is 2 to the 1st times 2 to the 14th. That's 2 to the 15th. And that comes out to be 32,768. So the question is now, that's the number of ancestors at generation 15. If we're going back 15 generations, I believe what we are now doing is finding the sum of the series, where you'd have n over 2 times first term plus the 15th term. So this is going to be very large, this number of ancestors here. And I'm moving my music source, so it's probably changing the sound a little, because my phone is both my music source and my calculator. I forgot to bring myself a graphing calculator this weekend. So 15 halves, 7.5. 7.5 times 32,770. Alright. That fruit fly has 245,775 ancestors. That's why there's so many bugs on this planet. And it's funny, you know, we think about our ancestors, a generation is like 25 years. But a fruit fly generation is what, a day? So that's like 2 weeks worth of fruit flies. That's kind of gross. Moving on. Okay. The orchestra section of a theater has 25 seats in the front row, 27 seats on the second row, 29 seats on the third row, and so on. The pattern continues until the 12th row. After that, every row has the same number of seats as row 12. So the first question is, how many seats are there in row 12? Well, we have A-N, so this is arithmetic, equals A1 plus N minus 1 times D. So A-N here is what we're finding for the 12th row, so we're finding A12. The first term, 25. 12 for N minus 1, the common difference, 2. So 25 plus 22. 11. 12 minus 1, 11 times 2, 22. 47 seats in row 12. So we need to find the sum of the first 12 rows. 25 in the first row, 47 in the last one. And that's going to be the number of seats in the first 12 rows of the orchestra. So 6 times 72. 252? No. That's not right. Fix that, Miss LeCount. Let's see. 6 times 70, 420. 6 times 2, 12. 432. So then we've got the rest of the rows that we're discussing. So 19 minus 12 is 5 rows. 5 rows times the maximum number of seats in that row, which is 47. So the maximum number of seats, not maximum number of seats. The maximum number is the same, or the number of seats in row 12, 13, 14, 15, 16, 17, 18, 19, the same. So 19 minus 12 gives us the excess rows, except apparently I cannot subtract. Come on. There we go. And then we'll have to add the 432 to that. So this is me being super lazy and putting in the calculator. 7 times 47, 329. Plus 432, 761 seats in the auditorium. All right, next question. Suppose a drop ball bounces back 4/5 of its original height. The ball falls from a height of 5 feet. It keeps on bouncing until someone picks it up. Estimate the total vertical distance the ball travels if no one picks it up. And so this is an infinite series. Super fast. This is 5 over a fifth. How many 1/5s are there in 5? Well, there are 25 of them, and that's the number of feet the ball will travel. Ooh, 30 seconds for one question. Okay, kids, sorry for the editing jump, and the music is coming back momentarily. Made a few mistakes on this one, had to go back and re-record. It's kind of a bummer, but it's okay. All right, new company hires an executive. The company is not expected to make a profit right away. So the executive agrees to an alternative payment scheme. The first month, he receives a penny. And then each month, what he makes doubles. So this is geometric until his annual salary meets or exceeds $2 million. Now, if the annual salary meets or exceeds $2 million, the monthly has to be at least $166,666.67. So that's the monthly salary required. Excuse me. To get to at least $2 million a year. Sorry about that. Probably contagious. You probably just yawned too. What's the total salary the executive receives in the first year? So I need, in order to figure that out, I'm going to need my series formula, 12 months worth, 1 penny for the first month, 1 minus r to the 12th power, r to the n, over 1 minus r. Okay? When I calculate that, when I go ahead and not r, it's silly, 2. 2 to the 12th power is 4,096. So negative 4,095 times 1 penny is going to be negative 40.95. And we're divided by negative 1, $40.95. Not bad for a year's work. Actually, it's pretty crappy. We know it's going to grow, but it's not going to grow that quickly. So after a year, he's not making anywhere near, or she is not making anywhere near. Oh, no, it does say his salary, so I guess it's a dude. Anyway, B. After how many months will the company start paying the executive the maximum salary under the contract? What we've got to do is figure out what number of months gives us this. Okay? So the first thing we do is divide by that penny. So we get this. And this is where you actually are going to need a logarithm. Because in order to solve this equation, you've got a variable in the exponent. In order to solve this equation, we're going to have to rewrite it so that it's not exponential. So it's going to be log base 2 of 16,666,667 is equal to n minus 1. And on your graphing calculator at school, you can do that no problem. I, on the other hand, cannot. I need to use the change of base formula. Now, we don't technically need to learn these things, and it's very frustrating for me that we kind of need it to figure out some of these problems. All right, so I've got my 166,666,000, that's not right. Clear. 16,666,667. All right, and I'm finding the log of that divided by the log of 2 comes out to n minus 1 equals 23.99, which is 24. All right, so it's 24 plus 5, 25 months. It's going to take 25 months to get to that maximum salary. What is the maximum annual salary? Well, if on the 25th month is the first time he gets to the point where he's going to make enough to make enough per year, he's still going to make more every month, that month, until the end of that year, right? So we want the, you know what, let's talk about this in class. I need to debate this with you because I'm not exactly sure how we would complete C. So let's look at our logarithms real quick in the next 2 slides and we'll be done. So we already know logarithm base b of a positive number x satisfies the definition. Log base b of x equals y if b to the y equals x. We can read log base b of x as log base b of x In other words, the logarithm y is the exponent to which b must be raised to get x. We've talked about these in class. The log base 10 of 1,000 is what exponent do you put on 10 to get 1,000? And there's a lot of good uses of logarithms, and I think what I wanted to do here is to talk about those uses, and then when we come to class, you're going to learn about the natural logarithm. I've got a great website for you to use. A common logarithm is a logarithm with base 10. You can write a common logarithm, log base 10, simply as log x without showing the 10. And this is what we use on the calculator, the base 10. Many measurements of physical phenomena have a wide range of values. The reported measurements are logarithms. They're exponents of the values, not the values themselves. You could use a logarithmic scale for things like the way a bacteria multiplies. When you use logarithmic scale instead of a quantity, you have a logarithmic scale. Logarithmic quantity instead of the quantity, you have a logarithmic scale. The Richter scale is a logarithmic scale. So when you hear that an earthquake was a 6 on the Richter scale as opposed to a 7, the 7 is 10 times stronger. Okay? The energy released is 30 times greater at each magnitude on that scale. That's kind of terrifying because a Richter, an 8, a 7 or 8 on the Richter scale is a very scary earthquake. Imagine a 9 or even higher. I don't know how high they go. Okay, I hope this didn't get too long, girls, and we'll see you in class, and we'll finish up that last problem and work on the natural logarithm. I forgot that last part. See you in class.